Hello there. Welcome to the Ancient Earth Documentary Podcast. 300 million years ago, something happened that would eventually power the Industrial Revolution, light up cities, and reshape human civilization. And it all started in a swamp. Not just any swamp, but vast, steaming wetlands that stretched across continents, filled with plants that looked nothing like what you'd recognize today. These ancient landscapes became the coal we burn, and the story of how dead plants turned into black rock is far stranger than you'd imagine. Right now, beneath your feet, potentially hundreds of feet down, there might be layers of compressed ancient forest. Entire ecosystems pressed into seams of carbon. The coal that heats homes, generates electricity, and fuels industries didn't form everywhere or at any time. It required a very specific set of conditions that Earth stumbled into during one particular chapter of its history. A chapter we call the Carboniferous period. The Carboniferous stretched from about 359 million years ago to 299 million years ago, 60 million years. To put that in perspective, dinosaurs existed for roughly 165 million years. The entire age of mammals, our age, has lasted only about 66 million years since the dinosaurs disappeared. The Carboniferous was a long era, and during much of it, Earth was a coal-making machine. Scientists named this period after the massive coal deposits it left behind. Carboniferous literally means carbon-bearing. When geologists first studied rock layers in England and noticed thick black seams running through the stone, they realized these represented something unusual. A time when organic material didn't just rot away like it does now, but accumulated and transformed into something entirely different. Here's what makes this remarkable. According to some estimates, 90% of the coal humanity burns today comes from that single geological period. Not from millions of years spread across Earth's history, but from one concentrated window of time. Think about that. Nearly all the coal that powered steam engines, steel mills, and power plants originated in swamps that existed before the first dinosaur ever walked. At their peak, coal forests covered roughly 20 million square kilometers. That's an area larger than Russia. Imagine standing at the edge of one of these forests. You'd see a landscape so alien it would feel like another planet. The plants towering above you wouldn't be oaks, pines, or maples. They'd be giant club mosses, some reaching heights of over 100 feet, tree-sized horsetails with segmented trunks, massive ferns with fronds spreading like umbrellas, and strange tall plants called chordates with strap-shaped leaves, distant relatives of modern conifers, but unlike anything in today's forests. These weren't the flowering plants that dominate modern landscapes. Flowers hadn't evolved yet. No roses, no grasses, no fruit trees. The Carboniferous forest was built by more primitive plants, experiments in how to grow tall and capture sunlight, and they did it remarkably well. Walk through this ancient swamp and the air would feel thick, humid, oppressively heavy. The temperature would be tropical, even near what we'd now call temperate zones. The entire planet was warmer then. No ice caps at the poles for much of the period. Rain fell constantly in many regions, feeding rivers that snaked through flat, waterlogged terrain. Your feet would sink into soft ground with every step. Water everywhere, shallow and stagnant, pooling between the massive trunks. The forest floor would be a maze of fallen logs, tangled roots, and decomposing plant matter slowly being buried under layers of new growth. Fungi would coat everything, though even they struggled to break down the tough, fibrous tissue of these ancient plants. The sounds would be different too. No bird songs, because birds didn't exist yet. No mammals scurrying through the undergrowth. Instead, you'd hear the buzz of enormous insects, dragonflies with wingspans stretching over 2 feet, millipedes as long as your arm crawling over rotting logs. The hum of life, but life built on a completely different template than what came later. This was Earth experimenting, trying out new forms, new strategies, and in the process, creating the conditions for something that would matter hundreds of millions of years later when a strange bipedal species figured out how to dig up and burn the remains of these forests. The plants themselves were bizarre. Take lepidodendron, one of the dominant trees. It looked vaguely like a modern tree from a distance, with a tall trunk and a crown of branches at the top. But up close, the differences became clear. The trunk was covered in a diamond pattern of leaf scars, creating a texture like reptile skin. The roots, called stigmaria, spread horizontally just beneath the surface rather than diving deep. And the tree grew in a strange way, shooting up rapidly, reproducing once, then dying. More like a giant weed than what we'd consider a proper tree, or consider calamites, the giant horsetail. Modern horsetails are small, barely knee-high plants you might find near streams. Their Carboniferous ancestors grew 20 meters tall with trunks 60 centimeters thick, segmented like bamboo with whorls of branches at each joint. Forests of these would have looked like something from a fever dream. The tree ferns were perhaps the most familiar-looking plants to modern eyes, but even they were different, larger, stranger, with trunks made not of wood, but of densely packed root tissue. And the seed ferns, which weren't true ferns at all, but an intermediate form between ferns and seed plants, added another layer of strangeness to this already alien landscape. What's crucial to understand is that these plants were built differently than modern trees. Their structure, their chemistry, the very way they grew, all of it was unique to this time. And that uniqueness played a direct role in why they became coal. Modern trees grow wood, proper wood, with lignin and cellulose, arranged in ways that give strength and flexibility. Carboniferous plants had lignin too, but in different proportions and configurations. Some had bark that was incredibly thick relative to their size. Others grew in ways that left them structurally weak but fast-growing. They were evolutionary experiments, and many of these experiments would eventually go extinct, outcompeted by more efficient plant designs. But before that happened, they had millions of years to grow, die, and pile up in the swamps. And that's where the real story begins, because it's not enough to just have lots of plants. Modern rainforests have enormous amounts of plant matter too, but they're not forming coal. The Amazon isn't going to become a coal seam. Something else was necessary, something about the environment itself that made the Carboniferous special. The swamps where coal formed weren't like modern swamps. They were flatter, more extensive, and fed by a climate system that dumped rain with relentless consistency. The central Pangaean Mountains, a range formed as the continents slowly crashed together into the supercontinent Pangaea, created a monsoon pattern that drenched the lowlands year-round. No dry season, just constant moisture, water levels rising and falling with glacial cycles far to the south, but never truly drying out. This created a landscape where rivers meandered slowly, depositing silt, changing course, creating natural levees that trapped water in vast, shallow pools. Lakes formed where the land subsided. Former swamps became dry land as silt built up. And through it all, the plants kept growing. The key was the water. Not just any water, but stagnant, oxygen-poor water that covered the forest floor. When a tree fell in a modern forest, bacteria and fungi attack it immediately. Within years, sometimes months, the wood rots away completely, recycled back into the ecosystem. But in the Carboniferous swamps, this didn't happen. The moment a plant died and fell into the water, it entered a different world. A world where oxygen was scarce. And without oxygen, the bacteria that normally break down dead plant matter couldn't work efficiently. The process slowed to a crawl. Instead of rotting, the dead plants began to transform into something else. The first stage of this transformation is called peat. It's not quite plant matter anymore, but it's definitely not coal. It's something in between, a soggy brown mass of partially decayed vegetation. peat forms slowly, about a millimetre per year under ideal conditions, which means that coal seam you might see in a mine, the one that's 2 metres thick, required 20 metres of original plant material. 20 metres of dead trees, fallen leaves, collapsed ferns, all piling up over thousands of years. And here's what makes it even more impressive. That 20 metres of plant debris took perhaps 20,000 years to accumulate. A coal seam 10 metres thick, which isn't unusual at all, represents perhaps 200,000 years of continuous plant growth and death in the same swampy environment. 200,000 years of stability. The land neither rising so much that it dried out, nor sinking so fast that it became deep water. Just the perfect balance, maintained by geological processes operating on timescales we can barely comprehend. Some coal seams are even thicker. 12 metres, 15 metres, each one representing an almost incomprehensible amount of time and organic material. Modern peat bogs in places like northern Canada or Sumatra can be 15 feet thick or more, and they've been accumulating for only about 10,000 years since the last ice age. The Carboniferous had millions of years to work with. This is the foundation of coal formation, the first critical ingredient. Massive amounts of plant material falling into oxygen-poor water, accumulating faster than it could rot away, slowly transforming into peat. But peat isn't coal, not yet. It's too wet, too soft, too full of everything that made it plant matter in the first place. To become coal, peat needs something else. It needs to be buried, compressed, heated, and fundamentally transformed over millions of years. The swamp that created it needs to be covered, sealed away from the surface world, and subjected to the immense forces that operate deep within the earth. And that's exactly what happened. But how it happened, why it happened, and what occurred during that transformation is where the story gets even more interesting. Because turning soggy plant matter into hard, black, energy-dense rock requires a process that's part chemistry, part physics, and entirely remarkable. The Carboniferous swamps created the raw material. What came next would forge it into coal. Part 1. Word count, 2,223 words. The burial began with water. Not the stagnant swamp water that had preserved the peat, but seawater, rising, advancing, flooding over the ancient forests with deliberate patience. During the Carboniferous, sea levels didn't stay constant. They rose and fell in rhythm with the glaciers that expanded and contracted at the southern pole. When those massive ice sheets grew, locking up water, sea levels dropped. The swamps thrived, spreading across newly exposed coastal plains. But when the ice melted, the ocean returned. And when it came back, it brought sediment with it. Picture the scene. A vast peat bog, perhaps hundreds of square miles, built up over 100,000 years of plant accumulation. Then the sea arrives. Not as a violent flood, but as a gradual encroachment. First, the outer edges go underwater. Then, over decades or centuries, the water creeps inland. The swamp dies. The trees, still standing, drown in salt water. And then comes the sediment. Rivers flowing into this advancing sea carry silt, clay, and sand. The material settles out in layers, spreading across the drowned peat like a burial shroud. First, a thin layer, then thicker. Year after year, century after century, the sediment accumulates. The peat, once at the surface, sinks deeper. 5 meters down, 10 meters, 20. The weight above it grows, and with that weight comes pressure. This is where coalification begins, the transformation from peat to coal. It's a process driven by 3 main forces: pressure from the overlying sediment, heat from the Earth's interior, and time. Enormous amounts of time. The pressure comes first. As more sediment piles on top, the peat gets squeezed. Water, which makes up perhaps 70 or 80% of fresh peat, gets forced out. The plant material compacts. that 20 meters of original plant debris that created 2 meters of peat, it compresses further. The structure tightens, pores collapse. What was once soggy and spongy becomes dense and firm. But pressure alone doesn't create coal. Heat is essential. And the deeper the peat gets buried, the hotter it becomes. Earth's temperature increases with depth, a phenomenon called the geothermal gradient. On average, temperature rises about 25 to 30 degrees Celsius for every kilometre of depth. Bury peat under 2 kilometres of sediment, and it experiences temperatures around 50 to 60 degrees Celsius. 3 kilometres? Maybe 80 to 90 degrees. This heat doesn't cook the peat like an oven. It transforms it through chemistry. The plant material that became peat was made primarily of 3 substances: cellulose, hemicellulose, and lignin. These are complex organic molecules, chains of carbon, hydrogen, and oxygen atoms linked together. Lignin, the woody stuff that gives plants their structure, has a composition of roughly 54% carbon, 6% hydrogen, and 30% oxygen by weight. Cellulose is about 44% carbon, 6% hydrogen, and 49% oxygen. Both contain significant amounts of oxygen and hydrogen relative to carbon. Coal, by contrast, is almost pure carbon. Bituminous coal, the common black coal burned in power plants, is about 84% carbon. Anthracite, the highest grade, exceeds 90%. So where did all that oxygen and hydrogen go? They were driven off during coalification through 3 main chemical processes: dehydration, decarboxylation, and demethanation, fancy terms for relatively straightforward chemistry. Dehydration removes water molecules, H2O, breaking them off from the organic compounds. Decarboxylation strips away carbon dioxide, CO2. Demethanation releases methane, CH4. Each of these reactions pulls hydrogen and oxygen out of the original plant material, leaving behind increasingly pure carbon. These reactions don't happen at room temperature. They require heat. And they require time. Lots of it. The first stage produces lignite, also called brown coal. This is peat that's been buried deep enough and heated enough to lose most of its water and some of its volatile compounds, but it still retains significant amounts of oxygen. Lignite is soft, crumbly, and has a low energy content. It's barely coal at all, more like compressed dirt, but it represents the first major transformation. Bury lignite deeper, heat it more, give it another few million years, and it becomes subbituminous coal. The carbon content increases, more oxygen leaves, the material hardens. It starts looking like what we recognize as coal: black, somewhat shiny, capable of burning with real heat. Keep going, more burial, more heat, more time. Subbituminous becomes bituminous coal. This is the workhorse of the coal world, the most abundant type, the one that powered the Industrial Revolution. It's hard, black, and energy dense. The carbon content has reached 80 to 85%. Most of the original plant structure is gone. What remains is a rock made almost entirely of concentrated carbon, with just traces of hydrogen, oxygen, nitrogen, and sulfur. But there's one more stage, the ultimate transformation. Anthracite. This forms only under extreme conditions, burial depths of perhaps 5 to 10 kilometers, temperatures exceeding 200 degrees Celsius, and sometimes additional pressure from tectonic forces. Mountain building events can push coal deposits sideways and downward, subjecting them to stresses that accelerate the transformation. Anthracite is over 90% carbon. It's hard enough to break glass. It burns with an almost smokeless flame and produces tremendous heat. In the United States, it exists only in northeastern Pennsylvania, where ancient mountain building events buried and squeezed the coal to its ultimate form. Each stage of coal represents progressively more extreme conditions. More burial, more heat, more time. and each stage reflects a fundamental chemical reality: the transformation of oxygen-rich plant matter into carbon-rich rock. Now, here's what makes this process remarkable. It's irreversible. You can't turn coal back into peat. The chemical changes are too profound. The molecules have been broken apart and rearranged at the atomic level. The oxygen and hydrogen driven off as gases are gone forever. Coal is fossilized energy, but it's energy that's been concentrated, purified, and locked into a form that can persist for hundreds of millions of years. And this transformation happened in darkness, complete darkness. Once the sediment buried the peat, no light reached it, no oxygen either. The environment shifted from the oxygen-poor swamp to something even more extreme: total isolation from the atmosphere. This anaerobic environment is crucial. If oxygen had been present, the organic material would have oxidized, burned away, decomposed completely. But sealed away beneath layers of rock, the peat transformed instead of disappearing. The process also produced byproducts. Remember those chemical reactions stripping away hydrogen and oxygen? They released gases, methane primarily, carbon dioxide, water vapor. These gases had to go somewhere. Some escaped upward through cracks and pores in the overlying rock. Some got trapped, creating pockets of gas that miners would later discover, sometimes explosively. Some dissolved into groundwater. The coal that remained was the solid residue, the pure carbon left after everything else had been driven away. What's fascinating is how much time this required. The initial burial might happen relatively quickly in geological terms, a few thousand years for sediment to cover the peat. But the transformation from peat to lignite takes millions of years. Lignite to bituminous, another few million. Bituminous to anthracite, that might require 50 to 100 million years under the right conditions. The coal we mine today from Carboniferous deposits began forming 300 million years ago. 300 million years of burial, heating, and chemical transformation, and not all peat became coal. Far from it. For coal to form, the burial had to continue uninterrupted. If the sea level dropped again before enough sediment accumulated, erosion could strip away the thin covering. The peat would be exposed, dried out, and eventually decompose. Many peat deposits formed during the Carboniferous and never became coal. They were lost to erosion or oxidation or geological disturbances that exposed them too soon. The coal deposits we have represent the survivors, the ones that got buried deep enough, fast enough, and stayed buried long enough to complete the transformation. This is why coal seams are often found interbedded with other rock layers. You might see a coal seam, then a layer of shale above it, then sandstone, then another coal seam, then more shale. Each coal seam represents a period when a swamp existed and accumulated peat. Each layer of shale or sandstone represents a period when the sea advanced and buried the swamp. The pattern repeats because sea levels rose and fell multiple times during the Carboniferous, driven by the growth and retreat of glaciers. Each cycle created another potential coal seam. Geologists can read these layers like a history book. The coal tells them swamp. The shale above it tells them shallow sea. The sandstone might indicate a river delta or a beach. Then another coal seam, swamp returned. The rock layers preserve not just the coal, but the entire environmental history of the region over millions of years. It's a record written in stone, and coal is one of its most important chapters. But here's the critical point, and the one that connects this ancient process to our modern world. Coal isn't just transformed plant matter, it's transformed solar energy. Every atom of carbon in coal was once part of carbon dioxide in the Carboniferous atmosphere. That carbon dioxide was absorbed by plants through photosynthesis, powered by sunlight. The plants used that energy to build their bodies. When they died and became peat, that energy remained locked in the chemical bonds of the organic molecules. When the peat transformed into coal, those bonds survived. They concentrated, they purified. When we burn coal today, we're releasing energy That's sunlight deposited in plants 300 million years ago. Energy that's been stored, compressed, and preserved through an almost incomprehensible span of time. Each lump of coal is ancient sunlight made solid. And the process that created it, this burial and transformation, happened on a scale that's difficult to grasp. Entire landscapes buried. Entire forests compressed into thin black seams. Millions of years of heat and pressure working to transform soggy plant matter into one of the most energy-dense natural substances on Earth. The coalification process reveals something profound about geology. The Earth isn't static. It's a machine that transforms materials over time. Peat becomes coal. Mud becomes shale. Sand becomes sandstone. Coral reefs become limestone. Each transformation requires specific conditions and enormous spans of time. But the transformations happen. They're happening right now, somewhere beneath our feet, in the dark, under pressure, over timescales that make human history look like a single breath. Understanding how peat became coal gives us the second piece of the puzzle. We know where the material came from, the Carboniferous swamps. We know what happened to it: burial, pressure, heat, chemical transformation. But there's still more to the story, because coal formation didn't happen uniformly across the entire planet. It happened in specific places, under specific conditions. And understanding why those places were special requires looking at something even bigger than swamps or chemistry. It requires looking at the shape of the Earth itself during the Carboniferous, the continents, the mountains, the forces that controlled where swamps could form and where they couldn't. That's where the story goes next. The Earth during the Carboniferous wasn't arranged the way it is now. The continents hadn't settled into their modern positions. They were still drifting, colliding, assembling into configurations that would have looked alien to us. And that continental arrangement wasn't just geography. It was destiny for coal formation. During the late Carboniferous, the supercontinent Pangaea was taking shape. The landmasses that would eventually become North America, Europe, Africa, and South America were grinding together, creating massive mountain ranges where they collided. The Appalachian Mountains, the Variscan Mountains in Europe, these weren't just scenic features. They were the result of continents smashing into each other with the full force of plate tectonics. Those mountains changed everything about how water moved across the landscape. When continents collide and mountains rise, they create what geologists call fallen basins. These are low-lying areas adjacent to mountain ranges, essentially giant depressions in the Earth's crust, formed by the weight and pressure of the mountains themselves. The crust bends downward under the load. And those basins? Perfect places for swamps. The central Pangaean Mountains, stretching across what would become eastern North America and western Europe, created exactly this situation. As the mountains rose, the land in front of them subsided. Rivers flowed down from the highlands, carrying sediment and water into these lowland basins. The water pooled, swamps formed, and because the basins were slowly sinking, those swamps could persist for millions of years, constantly accumulating plant material. But mountain building did something else equally important. It changed the climate. When you pile rock kilometers high into the atmosphere, you create a barrier for air movement. The central Pangaean Mountains intercepted moisture-laden air flowing across the equatorial regions. That air rose, cooled, and dumped its water as rain, year-round rain, torrential, endless rain that created a monsoon climate in the fallen basins. The kind of climate where swamps don't just survive, they dominate. Think about modern rainforests. They exist in specific climate zones where temperature and rainfall create the right conditions for explosive plant growth. The Carboniferous swamps were similar, except instead of being scattered around the equator, they were concentrated in these massive foreland basins adjacent to mountain ranges. The mountains made the swamps possible. The swamps made the coal. And here's where the puzzle pieces really start fitting together. Those basins weren't just wet, they were subsiding, slowly, steadily sinking as sediment piled on top of them, and the weight of the mountains continued pressing down on the crust. That subsidence created something geologists call accommodation space, room for sediment and organic material to accumulate without simply filling up and stopping. In a stable landscape, a swamp eventually fills with its own debris. The peat builds up, the water level drops, the swamp becomes drier, and finally, it's not a swamp anymore. It's just land. But in a subsiding basin, the floor keeps dropping. The swamp never fills up. It just gets deeper. More peat accumulates, more plants grow. The cycle continues for timeframes measured in millions of years. This is why coal seams can be so thick. A 10-meter coal seam represents perhaps 100 meters of original peat. That much organic material doesn't accumulate in a static environment. It requires the land itself to be moving, sinking, providing endless room for more debris. The map of coal deposits today reflects this ancient geography. The major coal fields of North America, the Appalachian coal region, the Illinois Basin, the Western Interior coal fields, all formed in foreland basins adjacent to ancient mountain ranges. The European coal fields, stretching across England, Germany, Poland, formed in similar basins on the other side of the same mountain system. The mountains rose, the basins sank, the swamps thrived, the coal formed. But there's another layer to this story, one that takes us even deeper into the mechanics of the ancient Earth. Sea level during the Carboniferous wasn't stable, far from it. At the southern pole of the planet, glaciers were growing and shrinking in massive cycles. When glaciers grow, they lock water away as ice. Sea level drops. When they melt, that water returns to the oceans. Sea level rises. And because the Carboniferous swamps existed in low-lying basins, these sea level changes had dramatic effects. When sea level dropped, coastlines moved outward. The swamps expanded. Rivers extended their reach across newly exposed continental shelves. More land became available for plant colonization. More swamps formed. More peat accumulated. When sea level rose, the opposite happened. The sea flooded back across the lowlands. The swamps drowned. Seawater buried the peat under layers of marine sediment. The swamp environment was replaced by shallow ocean. And then, when sea level dropped again, the process repeated. New swamps formed on top of the buried ones. This is why coal deposits often occur in multiple layers, separated by marine sediments. Each coal seam represents a period when the area was a swamp. Each layer of shale or limestone above it represents a time when the sea advanced. The cycles are preserved in the rock record like growth rings in a tree, except these rings span hundreds of thousands of years each. Geologists have counted these cycles. In some coal basins, there are dozens of distinct coal seams stacked on top of each other, each one representing a separate swamp that existed when sea level dropped, then was buried when sea level rose again. The pattern is so regular in some places that it's been used to reconstruct the timing of glacial advances and retreats in the southern hemisphere, thousands of kilometers away from where the coal actually formed. The continents provided the basins. The mountains provided the rain. The subsidence provided the accommodation space, and the glaciers provided the rhythm. Together, these factors created the perfect storm for coal formation. But there's one more piece that makes the Carboniferous special, something that wouldn't repeat in quite the same way ever again in Earth's history. The position of the continents placed enormous landmasses directly on the equator. The equator receives the most solar energy of anywhere on the planet. It's where photosynthesis can operate at maximum efficiency. And during the Carboniferous, huge expanses of equatorial land were covered by these swamp forests, all of them photosynthesizing at incredible rates, all of them pulling carbon dioxide out of the atmosphere and converting it into plant tissue. The scale of this carbon capture was staggering. Estimates suggest that atmospheric carbon dioxide levels dropped significantly during the Carboniferous, from perhaps 4 or 5 times modern levels down to something closer to what we experience today. Where did that carbon go? Into the swamps, into the peat. Eventually, into coal. This wasn't just local, it was global. The coal forests were removing so much carbon dioxide that they changed the entire planet's climate. Temperatures cooled. Glaciers grew at the poles. And ironically, those glaciers created the sea level changes that helped bury the peat and turn it into coal. The forests engineered their own preservation. Modern coal deposits don't form this way. We don't have the same continental configuration. We don't have the same climate patterns. We don't have the same types of plants. The Carboniferous was a unique moment in Earth's history, when everything aligned to create conditions perfect for massive coal deposition. It happened, it worked, and then it ended. By the end of the Carboniferous and into the Permian period, the climate began to shift. The equatorial belt became drier, the swamps shrank, the forests retreated, coal formations slowed dramatically. Later, geological periods would create some coal, yes, but nothing approaching the scale of what formed during those roughly 60 million years when the coal forests dominated. Understanding this geological context transforms how we think about coal. It's not just fuel, it's evidence. Evidence of ancient continents colliding. Evidence of mountains rising and basins subsiding. Evidence of sea levels rising and falling in response to ice sheets thousands of kilometers away. Evidence of forests so vast they change the composition of the atmosphere itself. Every coal deposit is a geological story written in carbon. The thickness of the seam tells you how long the swamp existed. The layers above and below tell you what happened before and after. The chemical composition tells you what kinds of plants grew there and how deeply the coal was buried. The geographic distribution tells you where the ancient basins were, where the mountains rose, where the shorelines lay. Geologists can reconstruct entire ancient landscapes by studying coal deposits. They can map where rivers flowed, where deltas formed, where the sea advanced and retreated. They can track the movement of continents over millions of years by matching coal seams across modern ocean basins that were once connected. Coal becomes a time marker, a snapshot of Earth's configuration at a specific moment in deep time. And all of this, the mountains, the basins, the sea level changes, the continental positions, had to happen in exactly the right sequence and the right places for coal to form. Change any one factor, and the outcome would have been different. The swamps might not have formed. The peat might not have accumulated. The burial might not have occurred. Coal formation required a convergence of geological circumstances that was rare even over the vast expanses of Earth's history. This is why coal deposits are geographically clustered. They're not randomly distributed across the planet. They follow the ancient geography of the Carboniferous world. The coal fields of Appalachia and Europe line up because they formed in the same foreland basin system, now split by the Atlantic Ocean. The coal fields of China and Russia formed in different basins, but under similar conditions created by the assembly of Pangaea. When you burn coal, you're not just releasing ancient sunlight. You're releasing the product of an entire planetary configuration that no longer exists. A world of colliding continents, rising mountains, subsiding basins, fluctuating seas and forests, unlike any that exist today. That energy has been locked away, waiting for 300 million years. The geological stage was set. The chemistry was understood. But there's still more to uncover about why the Carboniferous forests were so uniquely suited to becoming coal. The plants themselves had characteristics that modern forests don't share. And those differences weren't minor details. They were fundamental to why so much coal formed when it did, and why nothing quite like it has formed since. The trees themselves were strange. Not strange in the way a twisted oak or gnarled pine looks unusual, but fundamentally alien. If you could somehow step into a Carboniferous coal forest, you wouldn't recognize most of what you saw as trees at all. The dominant plants bore little resemblance to the woody giants that fill modern forests. They were evolutionary experiments in vertical growth, pushing the boundaries of what plant life could become when given the chance. Take lepidodendron, one of the most common coal forest trees. Scale tree, paleobotanists call it, because its bark was covered in a diamond pattern of leaf scars that looked like reptilian scales. These weren't small shrubs. They towered 30 meters high, their trunks a meter or more in diameter. But here's what made them strange. They barely had wood. Modern trees build thick cores of dense woody tissue, linen-rich heartwood, that supports their weight and transports water. Lepidodendron didn't bother. Its trunk was mostly bark, a thick corky outer layer surrounding a relatively thin cylinder of vascular tissue and a soft, spongy core. It was more like a giant asparagus stalk than an oak. The structural support came from the bark itself, rigid and thick, holding the tree upright through sheer stiffness rather than internal strength. This design had consequences. When a lepidodendron died and fell, it didn't rot like modern trees. The thick bark resisted decomposition. The soft interior might decay quickly, but the outer cylinder remained intact, a hollow tube lying in the swamp. These bark cylinders accumulated in enormous quantities, their waxy, resinous coating protecting them from the bacteria and fungi that would normally break them down. Even stranger was how they grew. Lepidodendron had determinate growth, meaning they grew to full height rapidly, then stopped. Unlike modern trees that can add growth rings year after year for centuries, these scale trees shot up to full height in perhaps a decade or two, reproduced once in a massive burst of spore production, then died, the entire tree dead, falling into the swamp. Every few decades, whole stands would reproduce simultaneously and collapse, dumping thousands of tons of bark-rich organic matter into the peat in a single event. Think about what that means for coal formation. Modern forests lock carbon away in long-lived heartwood. An oak or sequoia might live for centuries or even millennia, its carbon trapped in living tissue. But lepidodendron dumped its carbon into the peat on a regular schedule. A biological conveyor belt moving atmospheric carbon into the ground, at rates modern forests can't match. Then there were the calamites, the giant horsetails. If you've seen a horsetail plant today, those jointed green stems that grow in ditches and wet places, you know their basic architecture. Calamites were built on the same plan, but scaled up absurdly. 20 meters tall, trunk 60 centimeters thick, growing in dense stands along waterways and in wet lowlands. Like lepidodendron, they were hollow, their structure more scaffolding than solid wood. What's remarkable is how fast they grew. Modern horsetails are already quick-growing plants, pushing up new shoots in weeks. Calamites likely grew even faster, exploiting the high carbon dioxide and oxygen levels to build tissue at extraordinary rates. When they died, often seasonally as water levels fluctuated, they added another layer to the accumulating peat. Their hollow structure meant more surface area exposed to partial decomposition, more opportunities for carbon to be preserved rather than fully oxidized back to carbon dioxide. The tree ferns added another dimension. Ceronius, the most common coal forest tree fern, grew 10 meters tall with a crown of enormous fronds. But calling them tree ferns is misleading. They weren't trees with fern leaves. They were gigantic ferns, period. The trunk wasn't wood, but a mass of adventitious roots, thousands of rootlets wound together in a dense mat. As the plant grew taller, it kept adding roots at the base, the older roots dying and the newer ones taking over structural support. When a tree fern died and toppled, that root mass became part of the peat. Dense, carbon-rich, resistant to decay. The fronds would decompose relatively quickly, but the root trunk persisted, another contribution to the growing layers of partially decayed plant matter. Here's where it gets interesting. None of these plants had evolved the full complement of lignin that modern trees possess. Lignin is the complex organic polymer that makes wood woody, giving it strength and also making it extremely resistant to decomposition. It's so tough that only a handful of specialized fungi and bacteria can break it down efficiently, and even they take their time. But Carboniferous plants hadn't perfected lignin production yet. Their tissues contained simpler compounds, less complex polymers, that were easier for early decomposers to attack. You'd think this would mean faster decomposition and less peat formation. Here's the twist. The decomposers themselves hadn't evolved the tools to handle what lignin these plants did produce. White rot fungi, the organisms that can efficiently break down lignin today, didn't exist yet. Neither did the full array of bacteria that modern ecosystems deploy against dead plant matter. The Carboniferous was a time when plants had raced ahead of the decomposers, building structures that nothing in the environment could fully digest. The result was a massive imbalance between production and decomposition, with plant material accumulating far faster than the available organisms could process it. Add to this the physical structure of the coal forests themselves. These weren't open woodlands with widely spaced trees. They were dense, tangled jungles where plants grew in tight proximity, competing for light and space. When trees fell, they often fell into standing water, into oxygen-poor conditions where even the limited decomposers that did exist couldn't function effectively. The forest floor was a graveyard of partially rotted logs, collapsed fronds, shed bark, and accumulated leaf litter, all slowly compressing under its own weight into peat. The canopy structure mattered too. Unlike modern forests where tall trees shade out the understory, Carboniferous coal forests had multiple canopy layers, each capturing light and contributing organic matter. The tallest Lepidodendron and Cordaites trees formed an upper canopy 30 meters up. Below them, tree ferns and smaller scale trees created a mid-canopy. At ground level, a dense undergrowth of ferns, small club mosses, and herbaceous plants filled every available niche. When any level died back, it added to the accumulating biomass below. This vertical structure meant the forest was essentially a three-dimensional carbon capture machine, pulling carbon dioxide from the atmosphere at multiple levels and dumping it into the swamp as fast as the plants could grow and die. The sheer productivity of these forests was staggering, probably exceeding even the most productive modern tropical rainforests. But productivity alone doesn't make coal. Modern rainforests are incredibly productive, yet they don't form peat on anything like the Carboniferous scale. What made the coal forest different was the combination of high productivity with poor decomposition and perfect preservation conditions. Three factors that had to align simultaneously. The chemistry of the plants themselves contributed in ways we're still discovering. Many Carboniferous plants produced resins, waxes, and other secondary compounds as defenses against the giant insects and early vertebrates that were trying to eat them. These compounds were often toxic or unpalatable to decomposers, further slowing breakdown. The bark of Lepidodendron, for instance, contained aliphatic compounds that modern analysis shows were highly resistant to bacterial and fungal attack. Some coal forest plants also had unusually high ash content. Mineral compounds accumulated from the soil that remained behind when the organic tissue decomposed. This ash could alter the chemistry of the peat, making it more acidic or changing its nutrient balance in ways that further inhibited decomposer activity. Essentially, the plants were poisoning their own graveyard, ensuring that their remains would persist longer than they would in a more balanced ecosystem. The seasonal cycles of growth and death intensified everything. Many coal forest plants weren't evergreen. They shed leaves, fronds, or even entire branch systems in response to flooding, drought, or seasonal changes. Each shedding event dumped massive amounts of organic debris into the swamp simultaneously. The decomposer community, already struggling to keep up, would be overwhelmed by these sudden pulses of dead plant matter. Before they could catch up, another pulse would arrive. The system never reached equilibrium. Water chemistry played its part. The slow-moving, stagnant waters of the coal swamps were often acidic, stained brown with tannins leached from decomposing plants. This acidity suppressed bacterial activity further. It also dissolved minerals that would later precipitate out, creating thin bands of limestone or siderite within the coal seams, markers of brief periods when conditions shifted. Even the insects and early amphibians that lived in these forests contributed to coal formation in unexpected ways. Giant dragonflies and millipedes, some of the first animals to colonize the land, fed on plant matter and each other. But they were relatively rare compared to the biomass of plants. There wasn't yet a diverse community of detritivores, the insects and other invertebrates that in modern ecosystems help break down dead plant matter. The herbivores that did exist often focused on living plants, leaving the dead material largely untouched. This imbalance between plant productivity and animal consumption meant more organic matter made it into the peat intact. In modern forests, insects, fungi, and bacteria form a decomposition army that processes dead plant matter within years or decades. In Carboniferous swamps, that army was undermanned and poorly equipped, allowing plant material to persist for centuries before being buried and transformed. The result was forests unlike anything that exists today, ecosystems specifically configured to produce coal. Not intentionally, of course. Evolution doesn't plan ahead. But the combination of rapid plant growth, poor decomposition, and perfect preservation conditions created a brief geological window where organic matter accumulated faster than any other time in Earth's history. When you hold a piece of coal, you're holding the compressed remains of these alien forests, their strange trees and peculiar ecology frozen in carbon. The coal swamps weren't static. They pulsed with change, rising and falling to rhythms set by forces far beyond their soggy boundaries. Sea levels rose and fell like breath, each cycle transforming the landscape. When sea levels dropped during glacial periods, vast areas of continental shelf emerged as new real estate for forests. Rivers stretched across these exposed plains, carving channels and spreading sediment. The coal swamps expanded, colonizing fresh ground with their peculiar vegetation. But this expansion came with a clock attached. When the glaciers melted and seas rose again, salt water crept inland, drowning the forests. Trees died standing, their roots pickled in brine. The organic matter they'd spent decades accumulating got buried under marine sediments, sand and silt washing in from the advancing sea. This burial was critical. Without it, the peat would eventually oxidize, decompose, and return its carbon to the atmosphere. But once buried, sealed away from oxygen and locked beneath layers of sediment, the transformation could begin. This cycle repeated hundreds of times across the Carboniferous. Geologists can read these oscillations in the rock record as alternating bands of coal and marine shale, each layer representing a complete rise and fall of the sea. Some coal seams show evidence of multiple flooding events, thin bands of mineral-rich clay sandwiched between thicker organic layers. The forests would establish themselves, grow for thousands of years, get drowned by rising seas, then re-establish when waters retreated. Each cycle added another layer to what would become massive coal deposits. The timing of these cycles mattered enormously. If sea level rose too quickly, the peat didn't have time to accumulate to significant depths. If it stayed low too long, the upper layers of peat might dry out and burn in wildfires, or begin to decompose aerobically. The sweet spot was a gradual rise, slow enough that thick peat could form, but steady enough to ensure burial before decomposition caught up. The Carboniferous hit this sweet spot repeatedly, almost as if the planet was deliberately trying to make coal. But there's something else happening beneath these swamps that most people never consider. The land itself was sinking. Not from the weight of the forests, though that didn't help, but from tectonic forces operating on geological timescales. Many coal-forming regions sat in what geologists call foreland basins, depressions in the Earth's crust, created by the weight of nearby mountain ranges. As these mountains rose, the adjacent lowlands sagged, creating perfect catch basins for sediment and organic matter. This subsidence was essential. Remember, a coal seam meters thick represents tens of meters of original plant material. For that much material to accumulate without spreading out horizontally or building up above water level, the ground had to be sinking at roughly the same rate the peat was accumulating. It's a delicate balance, and the Carboniferous achieved it across vast areas. The basins subsided, the peat accumulated, and the cycle continued for millions of years. The Central Pangaean Mountains, formed by the collision of continents, created exactly this scenario across what's now the eastern United States and parts of Europe. Their weight depressed the crust, forming extensive lowlands that filled with swamps. Rainfall, trapped and intensified by the mountains, fed these swamps year-round. The mountains also shed sediment during floods, periodically burying the peat and starting the cycle anew. Without those mountains, we wouldn't have the Appalachian coalfields or the vast deposits of the Illinois Basin. Once the peat was buried, geology took over. The weight of accumulating sediment compressed the organic material, squeezing out water and beginning the transformation from peat to coal. This isn't a quick process. The first stage produces lignite, sometimes called brown coal, which still contains significant moisture and has relatively low carbon content. It's barely coal, more like compressed peat with delusions of grandeur. Lignite is soft, crumbly, and if you've ever seen it, distinctly unimpressive. Yet it represents millions of years of burial and compression. As burial continues and temperatures rise, lignite transforms into sub-bituminous coal. The carbon content increases, volatile compounds are driven off, and the structure becomes more coherent. This happens at depths of a few hundred meters and temperatures around 100 degrees Celsius. The chemical bonds in the organic molecules begin breaking and reforming, a process that releases water, carbon dioxide, and methane. Some of this methane escapes, but much remains trapped in the coal's structure, which becomes important much later when humans start mining it. Push the coal deeper, subject it to more heat and pressure, and it becomes bituminous coal, the workhorse of the coal industry. This is what powered the Industrial Revolution, what still generates much of our electricity, what you picture when someone says coal. It's hard, black, and breaks with a distinctive glassy luster. Bituminous coal forms at temperatures between 100 and 200 degrees Celsius, usually at depths of 1 to 3 kilometers. The carbon content reaches 80 to 90%, and the material has transformed into something almost unrecognizable from its plant origins. But there's one more stage, reserved for coal that gets buried deepest and heated most intensely. Anthracite forms under conditions approaching metamorphism, temperatures above 200 degrees Celsius, and pressures equivalent to several kilometers of burial. It's over 90% carbon, burns with almost no smoke, and rings like metal when struck. Anthracite is rare because few coal deposits get buried deeply enough to reach these conditions without being destroyed by even more intense metamorphism that would transform them into graphite. Each rank of coal tells a story of burial depth and geological history. The progression from peat to anthracite isn't just about carbon concentration. It's about time, pressure, and the patient work of geological forces acting over tens or hundreds of millions of years. When you hold a piece of anthracite, you're holding something that's been squeezed and heated to the point where it's barely recognizable as organic material. It's as close as buried plants can get to becoming diamonds without actually making the leap. The chemistry of this transformation is complex. The original plant material, rich in cellulose, hemicellulose, and lignin, undergoes a series of reactions collectively called carbonization. Dehydration removes water molecules from the organic structures. Decarboxylation strips away carbon dioxide. Demethanation releases methane. Each reaction increases the relative carbon content while reducing oxygen and hydrogen. The molecular structure shifts from the loose, irregular polymers of plant tissue to the more ordered, aromatic structures characteristic of coal. Temperature drives these reactions, but pressure plays a supporting role. Increased pressure makes certain molecular rearrangements more favorable, encouraging the formation of the dense, cross-linked structures that give coal its strength and burning characteristics. The combination of heat and pressure literally squeezes and cooks the organic matter into a new form, molecule by molecule, bond by bond. But coalification isn't uniform, even within a single seam. Variations in the original plant material, in burial conditions, in the presence of mineral matter, all create heterogeneity. A coal seam might contain bands of different rank, reflecting variations in the original swamp environment or in the burial process. Some areas might have been buried deeper or heated more intensely than others. This variation is why coal mining is as much art as science, understanding the character of each seam through experience and careful observation. Modern analytical techniques reveal details about coal that would have astonished earlier geologists. We can identify specific plant compounds that survived the transformation, molecular fossils that point to their biological origins. We can measure the thermal history of coal using chemical markers, determining how hot it got and for how long. We can even identify different types of organic matter within coal: vitrinite derived from woody tissue, inertinite from charcoal and degraded material, liptonite from spores and resins, each with its own properties and formation history. This microscopic view reveals coal as a complex archive of ancient ecosystems and geological processes. It's not just fossilized plants. It's a record of atmospheric chemistry, climate patterns, tectonic movements, and biological evolution. Each seam contains information about the world that existed when those plants were growing. Information we're still learning to read. The transformation from swamp to coal also trapped enormous amounts of carbon. During the Carboniferous, atmospheric carbon dioxide levels dropped significantly, pulled down by the rapid growth and burial of organic matter. This carbon removal changed the planet's climate, contributing to the glaciations that drove sea level changes and created the cyclical burial conditions that formed coal. It's a feedback loop, the formation of coal helping create the conditions that allowed more coal to form. When we burn coal today, we're releasing that ancient carbon back into the atmosphere, reversing a process that took hundreds of millions of years to complete. The carbon that those Carboniferous forests pulled from the air, that got locked away in swamps and buried beneath kilometers of rock, returns to the atmosphere as carbon dioxide. We're unwinding geological history, running the clock backward at a speed that would have been unimaginable to those ancient forests. The scale becomes staggering when you calculate it. Estimates suggest that 90% of the coal we burn today formed during the Carboniferous and early Permian periods, a window of roughly 100 million years. That means the vast majority of our coal reserves represent a specific, unrepeated moment in Earth's history when conditions aligned perfectly to bury organic matter faster than decomposition could return it to the atmosphere. It was an accident of evolution, ecology, and geology, a confluence of factors that existed briefly and then vanished. After the Carboniferous ended, coal formation didn't stop entirely, but it slowed dramatically. The evolution of lignin-degrading fungi meant organic matter decomposed more efficiently. The breakup of Pangaea changed climate patterns and sea levels. The diversification of insects and other detritivores created more efficient decomposition communities. Later geological periods produced some coal, but nothing approaching the massive deposits of the Carboniferous. That window closed, probably forever. Understanding this uniqueness helps explain why coal is such a peculiar resource. It's not distributed evenly across geological time or across the globe. Most of it formed in specific places during a specific era, concentrated in deposits that reflect the geography of an ancient supercontinent that no longer exists. When we extract coal from the ground, we're mining the remnants of tropical forests that grew near the equator of Pangaea, forests that covered regions which have since drifted thousands of miles from their original positions. The coal fields of Pennsylvania were once swamps at tropical latitudes. The deposits in Britain formed in equatorial wetlands that continental drift carried northward over hundreds of millions of years. The geography of coal tells the story of plate tectonics as much as it tells the story of ancient plants. This geographical concentration has profound implications for modern energy politics. Countries sitting on carboniferous coal deposits possess a resource that can't be recreated, while nations without these deposits must import or find alternatives. The Industrial Revolution began in Britain partly because British coal was abundant and accessible, lying in seams that could be reached without the deep mining techniques that would be developed later. Geography and geology conspired to place enormous energy reserves beneath a small island at exactly the moment when technology evolved to exploit them. History might have unfolded very differently if those coal seams had been located elsewhere, or if they'd been buried too deep to access with 18th century technology. The extraction process itself reveals how thoroughly coal formation changed the original organic material. When miners cut into a coal seam, they're not finding recognizable plant fossils. Occasionally, they'll discover the impression of bark or a fossilized trunk in the surrounding rock, but the coal itself is transformed beyond recognition. You can't look at a piece of coal and identify it as club moss or horsetail. The molecular rearrangement was too complete. What remains is carbon, compressed and chemically altered until it resembles its source material about as much as a diamond resembles the carbon dioxide that formed it deep in Earth's mantle. Yet sophisticated analysis can still tease out details about those ancient forests. Certain molecular structures survive coalification remarkably intact, biomarkers that point to their biological origins. Pristane and phytane, compounds derived from chlorophyll, persist through the transformation. Different types of plant tissues leave distinct chemical signatures. Spores and pollen can sometimes be identified microscopically in coal, tiny time capsules that survive the pressure and heat. These molecular fossils allow geologists to reconstruct not just what plants formed a particular coal seam, but what the environment was like when those plants were growing. Temperature is everything in coal formation, but not in the way you might expect. It's not about sudden heat, like throwing wood into a fire. It's about gradual, sustained warmth accumulated over millions of years. A coal deposit buried to a depth of 2 kilometers experiences higher temperatures than one buried at 1 kilometer simply from being closer to Earth's heat. That extra warmth, applied over geological time, drives chemical reactions that wouldn't occur at lower temperatures. The deeper the burial, the higher the rank of coal that eventually forms, assuming enough time passes for the transformation to complete. This is why anthracite deposits are relatively rare. Reaching anthracite rank requires either very deep burial or exposure to tectonic heat from mountain building. The anthracite fields of Pennsylvania formed when the Appalachian Mountains rose, folding and compressing older coal deposits while heating them through tectonic forces. That combination of pressure and heat drove qualification to its extreme, creating a carbon content exceeding 90%. Miners in those anthracite fields were extracting coal that had been cooked by mountain building, transformed by the same forces that lifted the Appalachians toward the sky. The physics of burial create predictable patterns. In a coal basin, deposits near the center typically reach higher rank than those near the edges, because central areas sink deeper and experience more heat. Geologists can map these patterns, creating contour lines showing how coal rank varies across a basin. These maps reveal the subsidence history of the basin, showing which areas sank fastest and deepest. They're geological cross-sections through time, showing how the basin evolved over millions of years. Mining operations must account for these variations. A single mine might encounter coal ranging from high volatile bituminous near the surface to low volatile bituminous at depth. Each rank has different properties, burning characteristics, and commercial values. High volatile bituminous coal ignites easily and burns with a long flame, making it ideal for steam generation. Low volatile bituminous burns, hotter with less flame, better suited for metallurgical applications. Miners have to know what they're digging into, not just where the coal is, but what kind of coal it is. The impurities in coal tell their own story. Sulfur content varies dramatically depending on the environment where the peat accumulated. Freshwater swamps produce low sulfur coal because sulfur compounds wash away in flowing water. Marine-influenced swamps, where seawater periodically flooded the peat, produce high sulfur coal because seawater carries dissolved sulfates that get incorporated into the organic matter. When that coal burns, the sulfur oxidizes into sulfur dioxide, the compound that causes acid rain. This environmental problem stems directly from the ancient swamp chemistry, a consequence of seawater intrusion that occurred hundreds of millions of years ago. Ash content similarly reflects the swamp environment. Clean coal with low ash content formed in stable swamps, where very little sediment washed in. Dirty coal with high ash formed in swamps that received regular flooding, depositing layers of silt and clay among the plant matter. These sediment layers became the mineral matter that remains as ash after combustion. Miners can sometimes see these variations with the naked eye. Thin grey bands running through the black coal, representing ancient flood events that interrupted peat accumulation. The presence of these sediment bands reveals something important about Carboniferous swamps. They weren't static environments. Rivers flooded regularly, depositing sediment before retreating. Storms pushed seawater inland, temporarily converting freshwater swamps to brackish environments. Tectonic subsidence varied across the basin, causing some areas to sink faster than others. All this variability got recorded in the peat and preserved through coalification, creating coal seams that are remarkably complex when examined closely. Modern coal use focuses almost entirely on its energy content, but historically, people noticed other properties. Some coals produce more smoke than others. Some leave behind clinker, fused ash that clogs furnaces. Some ignite easily, while others require sustained heat to catch. These differences aren't random. They reflect the specific plants that form the coal, the environment where they accumulated, and the geological history of burial and heating. A piece of coal is a record of hundreds of millions of years of history, compressed into something you can hold in your hand and set on fire. The irony isn't lost on geologists. We're burning archives, destroying the very records that could teach us about Earth's past. Each coal seam consumed is a chapter of Earth history that can never be read again. Yes, we've studied coal extensively and learned enormous amounts from it. But there's always more to discover, new analytical techniques revealing details we couldn't detect before. Every ton of coal burned is potential knowledge lost, information about ancient climates, ancient ecosystems, ancient atmospheric chemistry gone up in smoke. This tension between utility and preservation doesn't have an easy resolution. Coal-powered industrial civilization lifted billions of people out of poverty and continues to generate a significant fraction of global electricity. Those benefits are real and historically unprecedented. But so is the cost, not just in carbon emissions and climate change, but in the permanent loss of geological information. We're consuming in centuries a resource that took hundreds of millions of years to form, a resource that cannot be replaced on any human timescale. The formation process also explains why coal is such a dirty fuel. All those impurities, the sulfur, the nitrogen compounds, the mineral matter, they don't disappear when coal burns. They either escape as pollutants or remain as ash. Clean combustion is impossible because the coal itself isn't clean. It's a mixture of ancient organic matter and whatever else was in the swamp when the peat formed. Mineral sediments, dissolved compounds, trace metals, all locked together through coalification. Some of those impurities are actually valuable. Coal ash contains rare earth elements concentrated from the original plant matter. Germanium, gallium, and other metals exist in trace amounts, but in sufficient concentration that coal ash could potentially be mined for them. This idea of treating coal as ore rather than just fuel reflects a shift in thinking about what coal actually is. Not a pure carbon source, but a complex mixture formed from a complex environment. The methane trapped in coal seams presents both hazard and opportunity. During coalification, methane generated by chemical reactions remains trapped in the coal's porous structure. When mining exposes coal to lower pressure, this methane can suddenly release, creating explosive atmospheres that have killed thousands of miners throughout history. Modern mining carefully manages this methane, drilling relief wells and maintaining ventilation. But that same methane represents an energy resource. Coalbed methane, extracted deliberately before mining begins, provides natural gas from the same deposits that yield coal. It's another byproduct of coalification, another form of stored energy created by those ancient swamps. Understanding coal formation transforms how we think about energy. We talk about fossil fuels as if they're simple substances, but coal is anything but simple. It's a transformation of sunlight captured by plants that no longer exist, processed by bacteria and fungi that barely decomposed it, buried by seas that rose and fell, heated by burial that lasted longer than most mountain ranges survive, and finally exposed again by erosion or human excavation. Every step in that process had to work correctly, or coal wouldn't exist. Change any variable and the outcome changes completely. The Carboniferous created coal because everything aligned. Had the continents been configured differently, the tropical swamps wouldn't have been so extensive. Had fungi evolved their lignin-degrading capabilities earlier, the organic matter would have decomposed instead of accumulating. Had sea levels been more stable, the cyclical burial wouldn't have occurred. Had plate tectonics not buried the deposits deep enough, they'd still be peat instead of coal. The confluence of factors was precise and temporary. That's why coal formation essentially stopped after the Carboniferous. The window closed when conditions changed, and it hasn't reopened since. This makes coal a non-renewable resource in the most fundamental sense. We're not just using it faster than it forms. We're using something that isn't forming at all anymore, and probably never will again. The conditions that created coal were a one-time occurrence in Earth's history, a brief window when evolution, ecology, and geology aligned in a way that has never been repeated. Once we've burned through the Carboniferous legacy, that's it. There's no more coming. The economics of coal tell a different story than its geology. For most of human history, wood served as the primary fuel. Forests provided heating, cooking, and early metallurgy, but wood has limitations. It's bulky, relatively low in energy density, and when societies grew large enough, forests couldn't regenerate fast enough to meet demand. Britain faced this crisis first. By the 17th century, English forests had been so thoroughly depleted that wood became expensive and scarce. The country needed fuel desperately, and coal, which had been mined in small quantities for centuries, suddenly became essential. Early coal mining was brutal and dangerous. Miners dug shallow pits following coal seams that outcropped at the surface. As the easiest deposits were exhausted, they went deeper. Flooding became a constant problem. Ventilation was minimal. Methane explosions killed workers regularly. The technology of the time barely adequate for the task, but demand drove innovation. Newcomen's steam engine, developed in 1712, was originally designed to pump water from coal mines. That invention, born from coal's necessity, would eventually transform civilization. Coal powered the Industrial Revolution, not because it was clean or convenient, but because it was abundant and energy dense. A ton of coal contains roughly the same energy as 4 tons of wood, and unlike forests, coal deposits didn't need decades to regrow. Once you located a seam, you could extract it continuously until it ran out. This fundamental difference between renewable and non-renewable resources shaped economic development for centuries. The transition from wood to coal wasn't smooth or universal. Different regions adopted coal at different rates depending on geology and infrastructure. Britain led because it had accessible coal deposits and depleted forests. America, with vast forests still available, adopted coal more slowly. But wherever industrialization intensified, coal followed. Steel production required coking coal to smelt iron ore. Railroads ran on coal-fired steam engines. Factories needed reliable heat and power that only coal could provide at scale. Geography determined winners and losers in the coal economy. Countries sitting on major deposits gained enormous advantages. Britain's coal fueled its empire. Germany's Ruhr Valley deposits drove its industrial rise. America's Appalachian coalfields powered its growth. Nations without coal either developed different energy sources, imported it at great expense, or remained economically marginal. The distribution of Carboniferous swamps millions of years ago shaped 20th century geopolitics. Mining technology evolved rapidly once coal became essential. Deep shaft mining replaced surface extraction. Railroads connected mines to ports and factories. Entire towns grew around coalfields, populated by workers whose lives revolved around extraction. These weren't pleasant communities. Mining was dangerous work with high mortality rates. Black lung disease from coal dust inhalation killed miners decades after they'd stopped working. Mine collapses, explosions, and fires claimed thousands of lives annually. Yet people continued mining because the alternative was starvation. Coal mining towns offered employment where little else existed. Wages were low but regular. Company stores often trapped miners in debt, paying them in scrip redeemable only at inflated company prices. Labour conditions were so harsh that coal miners became some of the first and most militant unionised workers. The history of labour movements is inseparable from coal mining. The environmental cost of coal extraction only became apparent gradually. Early mining focused on accessible seams, but as those depleted, methods became more destructive. Mountaintop removal mining literally destroys mountains to reach coal seams, dumping millions of tons of rock into valleys and streams. The scale is difficult to comprehend until you see it. Entire landscapes transformed, ecosystems obliterated, watersheds permanently altered. Underground mining leaves its own scars. Abandoned mines collapse, causing subsidence that damages buildings and infrastructure decades later. Acid mine drainage occurs when water contacts sulfur-bearing minerals in exposed coal seams, creating sulfuric acid that pollutes streams and rivers. Some drainage sites will continue contaminating water for centuries without active treatment. The mines don't stop being problems just because they're no longer productive. Coal combustion releases carbon dioxide, but it also releases particulates, sulfur dioxide, nitrogen oxides, mercury, and other pollutants. Before environmental regulations, industrial cities were shrouded in coal smoke. London's infamous fog was actually smog, a toxic mixture of coal smoke and natural fog that killed thousands during severe episodes. The Great Smog of 1952 caused an estimated 12,000 deaths in just 5 days. That's not ancient history. That's within living memory. Sulfur dioxide from coal combustion combines with atmospheric moisture to form sulfuric acid, which returns to Earth as acid rain. In the 1970s and 1980s, acid rain damaged forests across northeastern North America and northern Europe. Lakes became so acidic that fish populations died out completely. Stone buildings and monuments eroded faster than they had in centuries. The problem was eventually addressed through regulations requiring sulfur scrubbers on coal plants. But the damage already done persists. Coal ash, the residue left after combustion, contains concentrated heavy metals and radioactive elements. A typical coal plant produces hundreds of thousands of tons of ash annually. This ash is stored in ponds or landfills, and when containment fails, the results are catastrophic. The 2008 Kingston coal ash spill released over 1 billion gallons of ash slurry, covering hundreds of acres and contaminating rivers. Cleanup took years and cost over $1 billion. Yet coal remained economically attractive because the costs were externalized. Power plants didn't pay for the health effects of air pollution. Mining companies didn't pay for watershed restoration. Nobody paid for climate change. When you don't account for external costs, coal appears cheap. Once you include those costs, the economics shift dramatically. The climate impact of coal is where past meets future most directly. Every ton of coal burned releases roughly 2.5 tons of carbon dioxide. That carbon was removed from the atmosphere during the Carboniferous and locked underground for 300 million years. We're re-releasing it in mere centuries. The atmosphere isn't responding gradually, it's responding abruptly. Carbon dioxide concentrations have increased from about 280 parts per million before industrialization to over 420 parts per million today. That increase correlates almost perfectly with fossil fuel combustion, and coal is the largest single contributor. The carbon isotope signature of atmospheric CO2 matches fossil fuel carbon, not volcanic or natural sources. We can trace the increase directly to coal and oil burning. The climate effects are no longer theoretical or distant. Global temperatures have risen over 1 degree Celsius since pre-industrial times. That might sound modest, but small changes in average temperature represent enormous changes in climate systems. Weather patterns shift, glaciers melt, sea levels rise. Extreme events become more frequent and severe. Coal plants are now being retired faster than they're built in most developed nations. Economics finally caught up with environmental reality. Renewable energy costs have dropped so dramatically that new wind and solar installations are cheaper than operating existing coal plants in many regions. Natural gas, while still a fossil fuel, produces about half the CO2 per unit energy compared to coal, and has displaced it in many markets. But globally, coal consumption continues. China, India, and other developing nations still build coal plants because they need reliable power and have domestic coal supplies. They're following the same development path that industrialized nations took, only now the atmospheric consequences are clearer. Telling countries not to use their coal deposits while having built prosperity on our own feels hypocritical, yet allowing continued expansion locks in decades more emissions. The future of coal isn't extinction, but decline. Existing plants will operate until they're uneconomical or regulated out of existence. Some coal will continue being used for steel production, where it's not just fuel but a chemical reagent. Anthracite may persist in niche applications, but the era of coal as the dominant global fuel is ending. What remains is the legacy. The carbon we've released will stay in the atmosphere for centuries even after emissions stop. Ocean acidification from absorbed CO2 will persist for millennia. The infrastructure built around coal, the towns, the mines, the power plants, will stand as monuments to a particular moment in human history when we discovered concentrated energy and used it without fully understanding the consequences. There's irony in coal's story. The Carboniferous forest grew in an atmosphere rich in CO2, pulling it down through photosynthesis and locking it underground. That drew down atmospheric carbon, contributing to ice ages and climate cooling. Now we're reversing that process, returning the carbon to the atmosphere far faster than it was removed. We're running the Carboniferous in reverse at a pace the planet hasn't experienced in hundreds of millions of years. The coal seams represent Earth's largest experiment in carbon sequestration. Nature found a way to take atmospheric carbon and store it permanently underground. That storage worked for 300 million years until we figured out how to reverse it. In a century and a half of industrial civilization, we've undone a significant fraction of what took 60 million years to accomplish. Some propose carbon capture and storage, attempting to recreate what the Carboniferous achieved naturally. Capture CO2 from power plants or directly from air, compress it, and inject it deep underground into geological formations. It's technically possible, but expensive and energy intensive. We're trying to engineer a solution to match what ancient swamps did accidentally through the simple fact of not decomposing. The comparison reveals something fundamental about our relationship with deep time. The Carboniferous didn't plan to create fuel for future civilizations. It wasn't storing energy for us. Those processes occurred because of specific biological and geological circumstances that happened to preserve organic matter. We've interpreted those deposits as resources, but they're really just accidents of Earth history that we learned to exploit. Understanding coal formation changes how we think about sustainability. Renewable energy isn't just about technology or economics. It's about working with Earth's current energy flows rather than depleting stored reserves from the deep past. Solar panels capture today's sunlight. Wind turbines harvest current atmospheric circulation. Geothermal taps ongoing planetary heat. These sources regenerate continuously because they're powered by processes still active. Coal, oil, and natural gas are different. They're geological fossils of ancient energy, one-time deposits that accumulated under conditions that no longer exist. Using them means spending down a savings account with no deposits being made. The account is large, but it's finite, and we're burning through it at a rate that would horrify any financial advisor. The Carboniferous gave us a gift and a test. The gift was concentrated energy that bootstrapped industrial civilization. The test is whether we're smart enough to transition away from it before the consequences become catastrophic. We're currently failing that test, though the outcome isn't determined yet. The question facing us now isn't whether we'll transition away from coal, but whether we'll do it fast enough to avoid the worst outcomes. Climate models show different scenarios based on how quickly we act. In the most optimistic projections, we phase out coal globally by 2040, cap warming at 1.5 degrees Celsius, and manage adaptation to the changes already locked in. In the bleaker scenarios, coal consumption continues for decades, warming exceeds 3 degrees, and we face cascading tipping points that make the climate crisis exponentially harder to manage. What makes this particularly urgent is the non-linear nature of climate systems. They don't respond gradually to forcing. They have thresholds where small additional inputs trigger large systemic changes, the collapse of ice sheets, the shutdown of ocean circulation patterns, the release of methane from permafrost. These aren't distant theoretical risks. They're mechanisms that become more likely with each fraction of a degree of warming. Coal plants built today will operate for 40 years unless we deliberately shut them down early. Every new coal-fired power station represents a commitment to decades of future emissions. China and India continue building coal capacity, despite also leading in renewable energy deployment. The economic logic remains compelling in countries where coal is cheap and domestic, even as the atmospheric consequences compound. Yet the transition is accelerating faster than most predictions suggested even a decade ago. Solar and wind have become the cheapest sources of new electricity generation in most markets. Battery storage is making renewables viable for baseload power. Electric vehicles are approaching cost parity with internal combustion. The technology for a post-coal world exists. What's required now is political will and massive capital deployment. Some argue we should keep burning coal while developing carbon capture at scale. Scrub the emissions, store the CO2 underground, and continue using fossil fuels indefinitely. It's technically possible but faces enormous practical barriers. Carbon capture requires significant energy, reducing the net output of power plants. Storage sites need geological stability and long-term monitoring. The costs remain high even as the technology improves. More fundamentally, carbon capture doesn't solve the problem so much as manage symptoms. We're still extracting stored carbon and returning it to active circulation, just with an attempted backstop. It's like proposing to solve overconsumption by developing better landfills rather than reducing waste. The approach might be necessary as a transitional technology, but it's not a permanent solution. The deeper issue is what coal represents in human psychology. For generations, it symbolized progress, wealth, and power. Mining communities built entire identities around extraction. Utilities-based business models on reliable fuel supplies. Countries measured development by coal consumption. Changing that requires more than technology. It requires reimagining what progress means. Some coal-dependent regions are managing this transition remarkably well. Germany's Ruhr Valley transformed from coal heartland to technology hub. Wales reinvented former mining towns as tourist destinations and renewable energy centres. These transitions weren't painless, but they demonstrate that communities can survive and even thrive after coal. What they needed was investment, planning, and recognition that the old model couldn't continue indefinitely. Other regions struggle more. Appalachia still hasn't recovered from coal's decline decades after mines started closing. Parts of Poland remain dependent on coal for employment and electricity. China faces the challenge of transitioning millions of workers while maintaining economic growth. The social costs of moving away from coal are real and concentrated, even if the benefits are diffuse and global. There's tragedy in how we're using the carboniferous gift. Those ancient swamps gave us concentrated energy that could have been deployed carefully to build a sustainable civilization. Instead, we're burning through it as quickly as possible, treating a one-time geological inheritance as an infinite resource. Future historians, if they exist, will likely view our era with bafflement. How could a species smart enough to understand climate science be too short-sighted to act on it? The answer involves timescales. Human cognition evolved for immediate threats and tangible rewards. Climate change operates on timeframes that feel abstract. The coal burn today causes warming that unfolds over decades and commits to impacts that persist for centuries. That disconnect between action and consequence makes it psychologically easy to defer action, to let the next generation handle it. But the next generation is already here, and they're inheriting the consequences. Young people today will spend their entire lives managing climate disruption we're causing now. The climate they experience in old age will be determined by decisions made in the next decade. That's not an abstract future scenario. It's a direct line of cause and effect, spanning a single human lifetime. Some climate scientists privately admit to pessimism. They've watched emissions rise despite decades of warnings. They've seen political promises evaporate. They understand the physics of climate inertia and know how much warming is already inevitable. Yet most continue their work because the alternative is giving up entirely. And the difference between 2 and 3 degrees of warming matters enormously for human and ecological outcomes. There's still time to avoid the worst scenarios, but the window narrows with each passing year. Every ton of coal burned today is a ton we'll need to compensate for later through more expensive and difficult methods. Every delayed decision makes the eventual transition more disruptive. The optimal time to act was decades ago. The second best time is now. What would an intelligent species do with the carboniferous legacy? Probably burn some of it to bootstrap renewable energy infrastructure, then leave the rest underground as a margin of safety. Use the gift to build the systems that make the gift unnecessary. Instead, we're racing to extract every accessible deposit, as if proving we can monetize all of it somehow validates the entire enterprise. The economic argument for continued coal use becomes weaker annually. Renewable energy costs keep dropping, while coal faces increasing regulatory pressure and competition. Insurance companies, recognizing climate risk, are withdrawing coverage from coal projects. Banks are restricting coal financing. The market is slowly recognizing what physics already proved. Burning fossil carbon at this scale is incompatible with a stable climate. Yet markets move slowly, especially when powerful interests resist change. Coal companies continue lobbying against climate policy. Utilities delay plant closures. Politicians in coal regions defend the industry even as employment dwindles. These rearguard actions buy time but can't change the fundamental trajectory. Coal is dying, killed by economics as much as environmental policy. The question is, how gracefully we manage that decline. Do we plan for it, supporting affected communities and accelerating alternatives? Or do we let it happen chaotically, with stranded assets and abandoned workers? The choice isn't whether coal ends, but how much damage occurs during its death throes. Looking back at the Carboniferous swamps, what strikes you is the accidental nature of coal formation. Those plants weren't trying to store energy for us. The geological processes that preserved them weren't designed for future extraction. It all just happened because conditions aligned in particular ways during a particular window of Earth history. We're the ones who assigned meaning and value to those deposits. That realization reframes the entire relationship. Coal isn't humanity's birthright or destiny. It's not proof of divine providence or validation of industrial civilization. It's just rocks that happen to burn, formed under conditions that no longer exist, useful for a brief period before the consequences of using them become unmanageable. We found concentrated energy and built a world around it, but that world was always temporary. The Carboniferous period itself offers an unexpected lesson about climate. Those coal swamps existed during a time of dramatic atmospheric shifts. CO2 levels dropped as plants pulled carbon down. Oxygen spiked to levels unseen before or since. The climate swung between greenhouse conditions and glaciation. Life adapted, but not without mass extinctions and fundamental ecosystem reorganization. We're now creating the inverse situation. Rapidly increasing atmospheric CO2, disrupting ocean chemistry, forcing temperatures upward faster than most species can adapt. The Carboniferous took millions of years to draw down carbon. We're putting it back in centuries. That difference in timescale matters enormously for biological and ecological responses. Some organisms will adapt, others won't. Ecosystems will reorganize around new conditions, but not in ways that preserve current biodiversity or human agricultural systems. We're conducting an experiment in rapid climate forcing without controls or the ability to reverse course if results prove catastrophic. The Carboniferous swamps didn't plan this. They just happened. We're the ones choosing to continue, despite understanding the outcomes. There's something almost cosmically ironic about coal's story. Ancient sunlight, captured by strange forests, compressed into rock. Discovered by curious primates, burned to power civilization, and ultimately threatening that civilization's survival. Each step seemed logical at the time. Each decision made sense given available information and immediate incentives. Only now, viewing the full arc, does the trajectory look insane. Future generations, assuming they exist, will study our era with the same fascination we bring to studying the Carboniferous. How did those conditions align? What made that period unique? Why did it end? Our answers will form their history, and coal will figure prominently. Not as fuel, but as the catalyst for a transformation we're still living through. The coal itself will remain underground for the most part. We'll never burn all of it. Economics and climate policy will strand most reserves before they're extracted. Those unburned deposits will sit there for hundreds of millions of years, just as they have for the last 300 million. Eventually, geological processes will bury them deeper or expose them to weathering. The carbon will rejoin the cycle through means we can't predict. Human response. Thank you for Part 8. Before I request part 9, I need to verify the word count, as it appears shorter than the required 2,222 words. Could you please 1. Provide the exact word count for the script you just generated? 2. If it's under 2,222 words, extend part 8 to meet the exact requirement. The script should be exactly 2,222 words, as specified in the requirements. In a few million years, assuming geological processes continue as they have, new coal deposits might form. Not from anything resembling carboniferous swamps, but from whatever organic material accumulates in oxygen-poor environments and gets buried under the right conditions. Modern peat bogs in places like Indonesia and Canada represent early stages of this process. Given enough time and burial, they could become coal seams for some distant future civilization to discover and debate using. But those deposits will be fundamentally different. The plant material comes from flowering trees and grasses, organisms that didn't exist during the Carboniferous. The chemical composition will reflect modern atmospheric conditions and different lignin structures. Future geologists will be able to distinguish Anthropocene coal from Carboniferous coal, the same way we can now identify different geological periods through their distinctive fossil assemblages and chemical signatures. This raises an uncomfortable question about legacy. What are we leaving behind? Carboniferous organisms left concentrated energy that powered technological civilization. We're leaving behind plastic in ocean sediments, concrete foundations, radionuclides from nuclear testing, and a drastically altered atmospheric composition. Our geological signature will be unmistakable, but not particularly useful to whatever comes after us. The coal industry itself is already becoming archaeological. Abandoned mines dot landscapes across Pennsylvania, West Virginia, Wales, and the Ruhr Valley. These structures are decaying into industrial ruins, gradually eroding back into the landscape they once scarred. In 1,000 years, most traces of surface mining will have weathered away. Underground tunnels will collapse and fill with groundwater. The massive machinery will rust into iron oxide stains. What remains longest will be the carbon we released. Atmospheric CO2 persists for centuries, some portion for millennia. Ocean acidification will take tens of thousands of years to reverse through natural carbonate buffering. Climate shifts we've triggered will echo through ecosystems for geological timescales. The real fossil record of the coal era won't be the mines themselves, but the chemical and biological disruption recorded in ice cores, sediment layers, and extinction patterns. There's something unsettling about the realization that coal's most lasting impact isn't the energy it provided, but the consequences of using it. The Carboniferous period created a battery. We discharged that battery in roughly 2 centuries. Now we're dealing with what happens when you dump massive amounts of stored chemical energy back into active circulation all at once. The mathematics of this are straightforward, but disturbing. Plants during the Carboniferous pulled carbon from the atmosphere over millions of years through photosynthesis. That carbon got locked underground for hundreds of millions of years. We're releasing it back in a geological instant. The biosphere has to reabsorb that carbon or adjust to its presence. An adjustment happens through ecosystem reorganization, which is a polite way of saying species die and new equilibriums emerge. Some organisms will thrive in warmer, more CO2-rich conditions. Others won't. Agricultural systems built around current climate patterns will require massive adaptation or relocation. Coastal cities will need to be abandoned or defended against rising seas. None of this is speculation. It's physics and chemistry playing out at planetary scale, driven by decisions made decades ago that we're only now fully understanding the implications of. The tragedy isn't that we used coal. Given the circumstances of early industrial development, the decision made sense. The tragedy is that we continued using it long after understanding the consequences. We've known about the greenhouse effect since the 1890s. We've had clear evidence of anthropogenic climate change since the 1960s. The delay between understanding and action represents a failure not of knowledge, but of will and institutional capacity to respond to slow-moving catastrophes. Coal companies knew. Internal documents from major fossil fuel corporations show they understood the climate implications of their products by the 1970s. They chose to fund disinformation campaigns rather than transition away from their core business. That choice, made by a relatively small number of executives and lobbyists, helped lock in decades of additional emissions and delayed meaningful climate action. The consequences of those decisions will outlast the companies themselves. This gets to something fundamental about how civilizations handle knowledge. We're extremely good at understanding systems in the abstract. We can model climate dynamics, predict emissions pathways, and calculate future temperature increases with reasonable accuracy. What we're terrible at is acting on that knowledge when action requires sacrificing immediate benefits for long-term stability. It's not ignorance that dooms us. It's the gap between knowing and doing. Coal represents the ultimate example of this gap. We know it's killing us. We know alternatives exist. We know every year of delay makes the problem harder to solve. And yet consumption continues, driven by economic inertia, political resistance, and the sheer difficulty of transforming energy systems that took centuries to build. The coal we're burning today was formed before dinosaurs existed. The consequences will persist long after our species is gone. Walking through a modern coal power plant offers a visceral sense of scale. Conveyor belts moving tons of crushed coal per minute. Boilers generating temperatures hot enough to melt steel. Turbines spinning at thousands of revolutions per minute. The engineering is impressive, the efficiency remarkable, and all of it exists to do one thing: boil water using ancient sunlight. When you reduce it to fundamentals, the entire system seems absurdly complicated for such a simple goal. But complexity is what happens when you optimize systems over time. Early coal plants were crude and inefficient. Modern facilities extract far more energy per ton of coal burned, with sophisticated pollution controls and heat recovery systems. Each generation of engineers improved the design, making the fundamental process more effective. What they couldn't engineer away was the basic chemistry. Burning carbon produces CO2. No amount of optimization changes that equation. Carbon capture technology represents an attempt to break that equation by separating CO2 from flue gases and storing it underground. The technology works, but the economics don't. Capturing, compressing, and sequestering CO2 requires significant energy, which reduces the net output of the plant. It also adds substantial costs that make coal uncompetitive with cheaper alternatives like natural gas and increasingly renewables. As a result, very few commercial-scale carbon capture facilities exist, and those that do often struggle with technical and financial challenges. Even if carbon capture became economically viable, it doesn't solve the fundamental problem. It just makes coal slightly less catastrophic. You're still mining finite resources, still disrupting landscapes, still producing waste ash and heavy metals. The captured CO2 still needs to be stored somewhere for thousands of years without leaking. You've traded an atmospheric problem for a geological storage problem, and the latter comes with its own risks and uncertainties. The more elegant solution is to stop burning coal entirely. This is happening gradually through market forces as renewables become cheaper and natural gas displaces coal in many markets. But it's not happening fast enough to avoid significant climate impacts. The gap between the pace of economic transition and the pace required by climate science represents the central challenge of this century. We're racing against physics, and physics doesn't negotiate. Some countries have made dramatic progress. The UK, birthplace of the Industrial Revolution, now goes days or weeks without burning any coal for electricity. Germany has closed many coal plants despite the economic importance of coal in regions like the Ruhr Valley. China, the world's largest coal consumer, has started investing heavily in renewables, though coal consumption continues to grow in absolute terms. The trajectory is clear, but the timeline remains uncertain. What happens to coal country when coal ends? This isn't abstract. Communities built around mining face economic devastation as plants close and jobs disappear. The promise of retraining and new industries hasn't materialized in most places. Former miners struggle to find work that pays comparable wages. Towns hollow out as young people leave for opportunities elsewhere. The transition away from coal creates real human suffering concentrated in specific places, even as it benefits the broader climate. This creates a political problem that transcends environmental policy. You can't tell people their livelihoods are being sacrificed for the greater good and expect them to accept it gracefully. Effective transition requires massive investment in affected communities, creating new economic opportunities and supporting workers through the change. Few governments have committed the resources needed to do this properly, which generates resistance and slows the overall transition. The irony is that many coal communities face health impacts from the industry itself. Black lung disease still affects thousands of miners. Air pollution from coal plants causes respiratory illness and premature death in nearby populations. Water contamination from mining operations persists for generations. The communities most dependent on coal are often the ones most harmed by it. Yet they resist transition because the alternatives offered are worse than the status quo, even if the status quo is slowly killing them. There's no easy resolution to this tension. Climate action requires phasing out coal. Economic justice requires supporting affected workers and communities. These goals can coexist, but only with substantial political will and financial investment. The failure to reconcile them represents a failure of governance, not a fundamental incompatibility of objectives. We know what needs to be done. The question is whether we'll do it. Looking backward from some hypothetical future, the coal era will appear as a brief but consequential period in human history. A few centuries of intensive extraction and combustion, sandwiched between millennia of pre-industrial existence and whatever comes after. The energy density of coal enabled technological civilization, but the side effects of using it threaten that civilization's continuation. Future historians will debate whether the trade-off was worth it, whether we could have done things differently, and why we took so long to change course, despite clear warnings. They'll study our era the way we study the Carboniferous. What conditions enabled this? What made it unique? Why did it end? The difference is, we have the ability to shape our ending in ways that lepidodendron forests did not. Those ancient trees simply grew and fell and accumulated, following biological imperatives without foresight. We can see what's coming. We can model outcomes. We can choose different paths. Whether we actually will remains the unanswered question of our time. Coal itself will persist long after we stop using it. The vast majority of deposits will remain underground, unburned and forgotten. Future geologists will find these seams and recognize them for what they are: compressed plant matter from an ancient world, preserved through geological accident. They might wonder why we burned so much of it despite understanding the consequences. The answer, when they piece it together from our records, will probably seem as strange to them as many historical decisions seem to us now. Obvious in hindsight, inexplicable in execution, very human in its short-sightedness. The coal in the ground represents a test we're currently failing, a test of whether a technological species can recognize and respond to the long-term consequences of its own success. The Carboniferous swamps didn't mean to create coal. They didn't plan for it to become fuel. They just grew and died, and happened to do so under conditions that preserved their carbon. We're the ones who dug it up, who burned it, who built civilization around it, and who now face the bill for that decision. How we handle that bill determines what comes next. The coal seams we've left unburned will outlast our civilization by hundreds of millions of years. Sitting in darkness, compressed and patient, they'll wait through whatever comes next. Mountains will rise and erode above them. Continents will drift. Species will evolve and go extinct. And those black layers of concentrated carbon will remain. Testimony to a time when Earth accidentally created fuel and humans accidentally discovered it. There's something almost poetic about that permanence. We treat coal as if it's temporary, something to extract and consume and move past. But the deposits themselves are more durable than empires, more lasting than languages, more permanent than any monument we've ever built. Long after the last power plant shuts down, long after the memory of the Industrial Revolution fades into archaeology, those coal seams will still be there, unchanged and unchangeable. What changes is the atmosphere above them. Every ton we've burned altered the composition of air that surrounds this planet. Carbon dioxide molecules don't care about human timescales. They persist for centuries, some portion for millennia, mixing through the atmosphere and dissolving into oceans, slowly working their way back into geological processes that operate on timeframes we can barely conceptualize. We release them in decades. Nature will take tens of thousands of years to fully reabsorb them. This asymmetry defines the challenge. Fast to release, slow to recapture, quick to disrupt, gradual to stabilize. We can alter planetary systems in a human lifetime, but those systems take geological ages to return to equilibrium. It's like pushing a boulder off a cliff. The push takes seconds. The boulder falling and the landscape adjusting to its impact takes far longer. And unlike a boulder, climate change isn't a single event. It's a cascade of interconnected disruptions, each triggering others in ways that compound over time. The mathematics are unforgiving. We've burned roughly half of easily accessible coal deposits. The other half remains underground, and every year we debate whether to leave it there or extract just a bit more. Economics pulls one direction, physics another. Short-term profit versus long-term stability. The same tension that's defined human civilization since we discovered we could reshape our environment to suit immediate needs. Coal didn't create that tension, but it exposed it with unusual clarity. Here's concentrated energy that took 300 million years to form, and we're burning through it in 300 years. 1,000 to 1 ratio. For every year of accumulation, 3 days of consumption. That ratio alone should give pause. When you're using a resource 1,000 times faster than it formed, you're not harvesting, you're mining. And what you're mining from isn't just the ground. It's the deep past, pulling forward energy that was meant to stay buried. Some argue this was inevitable, that any technological species discovering fossil fuels would use them, that the path from fire to coal to industrial civilization follows an almost deterministic logic. Maybe, but inevitability doesn't mean lack of choice. We chose how fast to burn coal. We chose whether to continue after understanding the consequences. We chose to prioritize immediate energy needs over long-term climate stability. Those were human decisions, not geological imperatives. The Carboniferous forests made their contribution to Earth's history completely unaware of what they were creating. They photosynthesized, grew, died, and accumulated. No planning, no foresight, no consideration of consequences. Just biology operating in an environment that happened to preserve rather than recycle. We have the opposite situation. Full awareness of what we're doing and what it means, yet somehow struggling to change course. That struggle reveals something uncomfortable about human nature. We're excellent at solving immediate, tangible problems, terrible at addressing slow-moving catastrophes that unfold over decades. Coal exemplifies this perfectly. The benefits arrived immediately: heat, power, industrial capacity. The costs accumulated slowly: air pollution, climate change, ecosystem disruption. By the time the costs became undeniable, we'd built entire economic systems around coal. Changing those systems requires dismantling infrastructure that took centuries to build, retraining workforces, and accepting short-term economic pain for long-term environmental stability. Most societies aren't good at that kind of trade-off. We discount future costs heavily. We prioritize present benefits. We assume technology will solve problems we create, even when the solutions don't exist yet. These aren't flaws unique to coal. They're features of how humans think about time and risk. Coal just happens to be the clearest example of where those cognitive patterns lead when applied at civilization scale. The transition away from coal is happening, but it's happening through economic displacement, more than environmental consciousness. Renewables became cheaper. Natural gas became more accessible. Coal became uncompetitive. Markets are solving what politics couldn't, though far too slowly for climate stability. This creates an odd situation where we're phasing out coal not because we've collectively decided it's wrong, but because alternatives became more profitable. The motivation matters less than the outcome, perhaps. But it does suggest we're not actually learning the deeper lesson about resource use and long-term thinking. What is that deeper lesson? Maybe that concentrated energy sources create civilizational dependencies that are extremely difficult to escape. Coal enabled industrialization, but it also trapped us in carbon-intensive infrastructure that persists decades after we understand its problems. We built cities around coal. We designed transportation systems assuming cheap energy. We structured economies on the premise that exponential growth could continue indefinitely. All of those assumptions are now being tested, and the infrastructure built on them can't be easily retrofitted. Future energy systems will hopefully avoid this trap. Renewable energy is distributed rather than concentrated. It can't be monopolized or depleted. You can't run out of sunlight or wind. Those resources regenerate continuously because they're powered by ongoing physical processes rather than ancient geological accidents. This fundamental difference might create more resilient, less path-dependent energy systems, or it might just create different problems we can't foresee yet. History suggests betting on the latter. The coal deposits we leave behind will become curious anomalies in Earth's geological record. Future geologists, whether human or otherwise, will find these carbon-rich layers sandwiched between other sediments and wonder about the conditions that created them. They'll reconstruct the carboniferous swamps, the strange plants, the unusual atmospheric chemistry. They'll piece together the story of how organic matter accumulated faster than it could decompose, how burial and heat transformed it into rock, how one brief period in Earth's history created the majority of concentrated carbon deposits. And if they're thorough, they'll also find evidence of rapid extraction. The missing coal, where seams once existed, the chemical signatures of mass combustion in atmospheric records, the climate disruption that followed. They'll see the full cycle: formation, preservation, discovery, extraction, combustion, consequence. A complete story written in stone and ice and sediment. The question they'll ask is whether the species that did this survived its own success. We're still writing that answer. What the Carboniferous gave us wasn't just energy. It was a test of foresight and restraint. Could we find concentrated power and use it wisely? Could we recognize when continued extraction became counterproductive? Could we transition away before the consequences became catastrophic? We're still in the middle of that test. The results aren't final, but the trajectory doesn't inspire confidence. Coal will outlast our civilization. The deposits we never burn will sit undisturbed for hundreds of millions of years, waiting for geological processes to either bury them deeper or expose them to weathering. Either way, that carbon will eventually rejoin the active carbon cycle through natural processes operating on timescales that make human history look like a brief flash. The planet will continue regardless of whether our species does. Earth has weathered far worse disruptions than anything we can cause. It survived asteroid impacts, supervolcanic eruptions, and mass extinctions that killed most existing life. Climate change driven by coal combustion is serious for us and for current ecosystems, but not for the planet itself. That perspective is simultaneously comforting and disturbing. Comforting because it suggests resilience and continuity beyond human timescales. Disturbing because it reminds us how little our existence matters to geological and evolutionary processes. We're here briefly, making noise and burning things, disrupting systems that will outlast us by millions of years. The Carboniferous forests didn't know they were creating our test. We won't know what test we're creating for whoever or whatever comes after. The coal in the ground will be their inheritance, along with whatever climate and ecosystems emerge from the changes we're causing. Those future inheritors might curse us for burning so much, or thank us for leaving some behind, or simply regard it as ancient history, no more relevant to them than the Carboniferous is to us. They'll live in whatever world results from our choices, and they'll make their own choices about how to use or preserve what remains. There's no moral to extract from coal's story that doesn't sound trite. Use resources carefully. Think long-term. Don't consume faster than systems can regenerate. These are obvious lessons that we collectively ignore because short-term incentives push the opposite direction. Knowing what to do and doing it are separated by the enormous gap between individual understanding and collective action. We're very good at the former, historically terrible at the latter. So the coal seams wait. Some will be burned in the coming decades as we gradually transition away. Most will remain untouched, too deep or too expensive to extract economically, protected by market forces if not environmental policy. They'll sit in darkness. Those compressed forests from an alien world, holding sunlight from before dinosaurs existed. Eventually, geological processes will either destroy them through metamorphism or expose them to erosion. The carbon will scatter back into the cycle, oxidizing slowly over millions of years, returning to the atmosphere through weathering rather than combustion. By then, humans will be long gone, replaced by whatever evolution produces next. Maybe something descended from us, maybe something entirely different. Life persists and changes and adapts to whatever conditions exist. The Carboniferous swamps proved that. They thrived in an atmosphere that would suffocate us, with oxygen levels that would make modern forests explode in flame. Yet they grew and spread and eventually created the coal that powered our brief moment of industrial civilization. The story comes full circle in a way. Ancient life created conditions for future life to exploit. We exploited them and in doing so created new conditions that future life will have to adapt to or exploit in turn. It's all just chemistry and biology and geology playing out over deep time, with brief pulses of what we call civilization appearing here and there, burning through concentrated energy, then fading back into the long story of planetary change. Coal was never really about coal. It was about what happens when you find concentrated power and lack the wisdom to use it carefully. That story repeats across human history in different forms. Forests cleared faster than they could regrow. Fisheries depleted faster than fish could reproduce. Aquifers drained faster than rainfall could refill them. The specific resource changes. The pattern remains constant. We find something useful, exploit it intensively, deal with consequences later, if at all. Breaking that pattern requires more than technology or policy. It requires fundamentally different thinking about time, about consequences, about our relationship with systems that operate on scales beyond human lifetimes. We need to care about outcomes we won't personally experience. We need to prioritize stability over growth. We need to recognize that some resources shouldn't be fully exploited just because we can. The coal in the ground offers a final chance to demonstrate that capacity. We could choose to leave most of it there. We could transition to renewable energy, not because it's profitable, but because it's necessary. We could accept the economic disruption of phasing out coal in exchange for climate stability. These choices are available. They're just hard. Harder than continuing business as usual. Harder than prioritizing quarterly profits over century-scale outcomes. Whether we make those choices determines what story future geologists tell about this era. Did we recognize the test and pass it? Or did we fail, burning every accessible deposit despite understanding the consequences, driven by short-term thinking that ultimately undermined the civilization it was meant to serve? The answer isn't determined yet. We're still writing it with every power plant we build or retire, every coal mine we open or close, every ton we burn or leave buried. The Carboniferous swamps wrote their chapter 300 million years ago. They created the conditions for ours. What we write now determines what comes next, if anything does. The coal will outlast whatever decision we make. It doesn't care whether we burn it or preserve it. It just sits there, compressed carbon from an ancient world, waiting with the patience that only geology knows, holding secrets about Earth's past and possibly humanity's future in every black glittering seam.